So today I'm going to continue with this R exercise, but I will not run a lot of things, but I will show you some things. The reason that
I'm
I
fine.
want to, is there a question?
Sorry.
Oh, okay, sure, no worries. The reason that I don't want to run them because every run takes a long time. So I make screen captures of the result so you can still compare them. So here, earlier section, we were paying attention on how to assess clustering tendencies. And now with our data, we have mixed data type. We're not all numerical. The data is not all categorical. We have mixed data. So for that kind of data, Galois distance is used. And Galois distance is exactly what we discussed at the very beginning of the class when we talk about distance measures. And how do we compute distance of two observations which are described using mixed type of variables. This basically is the weighted sum of each variable's similarity to the other observation. So variable by variable, we compute the similarity. And Galois actually does and scale the distance between 1 and 0, and then use a weighted sum. If user does not specify the weight, it will be, every variable going to have an equal weight. So if you use Galois, the distance is already normalized. So it's within 1, 0. So we don't have to do additional scaling. And also when we look at, when we talk about clustering algorithm, we mentioned the clustering algorithm don't do well with incomplete incomplete observation or observation with missing data. So we need to remove those. So currently the shooting should only have observations with complete data for each variable. And then we did the Euro selection, and all those are not really critical because we discussed those before. What I want to show you with this example are two things. One, we have lots of factors in our data. So I'm going to load the data so we can still see what we have. And some of our, I'll run one more step. Convert everything to factors. Okay, so at this point, we can look at our data. What do we have? You will see we have numbers and we have lots of factors. And lots of our factors actually are ordered. For example, population level from very low to medium to high. Age group from young, very young to young, and all that. So I'm going to demonstrate here that when you have factors and you can actually convert those factors to a data type called ordered factor. And the distance computation going to give you different results using ordered or unordered factors. So we're going to, in the following of the result, I'm going to compare the result with when using regular factor as a data type. Compare those two after we converted certain factors to ordered. So we converted the age, population level, and poverty level to ordered. As I suggested, I'm not going to run those because eventually I will not be able to get the results through this real data because it takes a long time. But I will show you what the difference. So keep that in mind. We're going to compare. So here are one set of results compare before using order factors and after using factors. So the first step I do when we do clustering again is check out clustering tendency. So we look at our data. So from our data, we ran DISI to get Galois distance. So this is a distance matrix, right? And we wanted to know whether our data actually have clustering tendency. The methods we have learned so far all required numerical data. We have mixed data, but that won't stop us because we, again, can use the ordered distance matrix idea. This package gave you a method that you can visualize your distance matrix, and you can ask the algorithm to order your data points so closer points are put together. So I used our distance matrix. Remember, even we have mixed data type, we can still use Galois to compute similarity. So we have this distance matrix. So using that, it gave us, I'm going to show you the result. Running this probably going to take 2 hours. I was able to run it last year, but I was not able to run it this year. So I'm going to show you the result. This is the result before using ordered factors that I obtained from last semester. Last semester, we didn't have poverty ratio level, but that doesn't really change much of the result. I'm going to just close this to make it less confusing. So this is the first was before, right? Before we're using ordered. And now after we're using ordered, what do you think? What difference do you expect to see? Do you see my browser window?
Yes.
Okay, good. So compare this. This is before when we use unordered factors. This is after we use ordered factors. What is the difference? Do you see? The difference I see here is we have stronger clustering, larger clusters after we used ordered distance. Before the factors are ordered, we have very, very little. We have small, very relatively small clusters and quite a bit of randomness. Here we have some very small clusters, and here probably can still observe as one clusters, and rest of it is rather random. And here we have pretty large clusters. So it makes sense when we actually use the factor as ordered, we give the algorithm more information. The algorithm knows that 1 is closer to 2 than 1 is closer to 3. Before we make it ordered, everything is different. 1 is different, completely different from 2, 1 is completely different from 3. So when we use ordered factors, you can see the clustering effect is that are going to become more similar, the observations. Here we have demonstrated using ordered distance matrix to observe the clustering tendency. And our findings here will be further confirmed if we actually run using t-SNE, again, you can use our distance matrix. When you supply it a distance matrix, t-SNE will just use this distance without having to use the method that you saw in the video to compute the distance. Maybe we can check this again. Before, let's close this too. So this is before t-SNE result. So you see separate clusters, and after t-SNE result. So you will see data is more like clustered together. We see 1, 2, maybe 3 clusters. And here before we see many small clusters. So which one is good? Which solution is better? Oh gosh, that's a really hard question to answer. So next I did PAM clustering. So here again we use our distance that we have computed. We turn it into a matrix. And here with the matrix you can find data points that are most different. So the observations in our data that are most different. And you can also retrieve data two pairs that are most similar in our matrix. And next, what I did is to actually start to do PAM, because I don't know how many clusters I might need. So I ran it from 2 to 20. And every time when I run this PAM, so this says we're using distance matrix. So because our distance is a distance matrix, it's not the original raw data matrix. That's why we need to say this is true. We find a clustering result. We save this clustering. This is Silhouette information, average width. We save that information in this array or list. Doesn't matter. And now we can plot this, plot 1 to 20. And here again, this is our result. Because I don't want to spend time running it, I saved the result from last run. So this first set of link is the run that I generated last semester when we don't have victim poverty ratio. This is a fresh result that we obtained this time. So we're going to look at this. Before using the ordered factors, the Silhouette plot looks like this. So from this, we can see which one gave us the largest Silhouette width. Maybe here, right? 17, 15. After we use the ordered factors, we get this. Looks to me very clearly 2 cluster is the best solution. So you can see that here it's very clear that using ordered and not ordered factors going to give us quite dramatically different result. So which one is the result that you want to trust? What you often would do is to use this to find summaries for each every cluster, and then see whether those clusters, the summary provides a clear explanation why points are put into different clusters. Those clusters can be clearly differentiated, whether those clusters match some known knowledge that you already have. When I did this quick analysis, I personally found cluster of 2 make more sense. When I have cluster 17, the differences are really very small that I can't tell why this small difference would separate large group of data into smaller pieces. So that's the key things that I want to show you using what we have learned so far on clustering. I'm going to switch now. If you have questions, this is the time to ask.
Could you step through the one with the 2 clusters, what it looks like, and why a little more detail on why that made more sense?
The pictures?
No, in terms of, like you said in the it was more explainable. Or,
okay. So when you do the summary, you should run this code. The summary tells you for every attribute. What's for a numerical value, it tells you the average, the standard deviation. For categorical value, it tells you mode. You can tell by comparing attributes one by one how one cluster is different from another. So what I'm saying that with the 17 clusters, those summary statistics on those attributes, on each of the, how many attributes we have here? I think 15 or something like that. It doesn't, I have a very hard time to interpret the result. The difference is very small, and all those clusters are put into different clusters with very small differences. When I used 2, it was much easier. It was a little bit easier. First of all, you only have 2 things to compare to, right? You compare one thing to another. And the distance among those attributes are actually a little bit larger. I don't exactly remember what was the key things that separate, but I don't think it was along the line of race. Oh, actually, oh, I should, yeah. Hold on, I think we can do one thing at least. That shouldn't take too much time. So the next point I want to make is because we were interested in race, right? We want to see whether race is actually
Sorry, just a follow-up question. So first we do the silhouette, and then sort of to validate these, we do the descriptive statistics just to kind of give us confidence that yes, these are in fact different.
Right. Eventually, when you have your clusters, you want to know what in every clusters. Ideally, if you could label these clusters, that will be perfect. So if you're actually doing clustering as standalone application, that would be your ultimate goal, to see what different clusters represent. On the other hand, if you do clustering as one pre-processing step for another mining task, then you can just simply use clustering numbers. This is cluster 1, this is cluster 2, using those as categorical features for your next text mining task. So I'm going to run this. So this is not going to take too much time. We're going to, so the evidence earlier that we received is either 2 or 15 or 17 clusters. So I'm going to use 2 to run this. Oh gosh, we didn't run this distance. Okay, let's go find the distance line and run the distance. Okay, here. So here is what we get, the Gower distance. And I'm going to use that distance to create a 2 cluster clustering.
Just curious what that warning message means.
Yes, right. So we have 2 logical variables. So those are binary variables. In DAISY, so Gower, when you supply logic variables, it will assume it's asymmetric. If you don't want the system to assume it to be asymmetric, you can actually convert those 2 factors. Convert those variables to factors. Our variable 5 and 8, I think, makes sense to be treated as asymmetric. Those variables are whether wearing, have sign of mental illness or wearing body cameras. Vast majority of them doesn't have sign of mental illness. Vast majority of the policeman was not wearing the body camera. So it was meaningful for the system to treat it as asymmetric. So this warning doesn't hurt anything. If you don't want the system to treat those variables as asymmetric, you can convert them into factor. Okay, so we have the PAM-FIT, and then we're doing the summary, and then what I want to do is to use, use the t-SNE to visualize, using again the same distance matrix to visualize our cluster. It's going to take a bit of time. Even faster, please. Oh well. I should have saved this picture. I don't know if I saved it. Oh, okay. So I did that. So what I want to show you is how the race I represented in different clusters. So here I used the t-SNE object y, which is the coordinates of the data points that are going to be plotted in this scatter plot. I'd convert it to data frame and set the name x and y axis. And I add a cluster attribute to this. And the cluster going to be used in our visualization as the color. So different cluster are going to be assigned different color. So in this case, I want to see how race was distributed in the data set. So that's why I used this race as the value for the cluster. So I can do this now. And with that, we can start a ggplot, a scatter plot. So as you can see, our this AB orders represent different factors, different races, and they are distributed in different clusters. Oh, I should remind you, we didn't do the convert to ordered. So this is unordered factors. So it gives us many small clusters, but in every cluster, we can see mixed of the races. So our race are represented in every cluster. Another way of saying this, these clusters were not established based on the race. Okay, so I think that's all the points that I want to make through this demonstration. Yes. And now we can move on to talk about today's topic.